So here's an image of a final created image on the right-hand side, so a particular image that was generated, and then its parents, shown just to the left and slightly smaller, half size. The grandparents, shown one column left of that, and half the size, and the great-grandparents and the great-great-grandparents, and so on. So all the way back till you have, I don't know, whatever it is, 6 generations here of predecessor images or ancestor images that were combined together through various generations to produce this image all the way on the right-hand side. And you can kind of see, as you go from the largest image and follow the lowermost branch, that there's a real family resemblance among these images, right? But they've brought in elements from the other images that they were crossed with. So that's kind of an interesting way to look at these things. As I said, I looked at a lot of these images, hundreds of thousands over a long period. And after a while, you do start to see that maybe you've seen what there is to see, right? There's a lot of possibilities, but they definitely come in families. So you can see repeated motifs here cropping up over and over again. And maybe it's because I was ruling out things that I didn't find interesting or attractive. But after a while, I did find that it was getting fairly repetitive. And so there wasn't much new, in my eye, coming out of the system. And so there was nowhere to go but up, right? I mean, this is all two-dimensional stuff. There is, of course, the possibility that instead of doing polar coordinate transformation, you could do some 3D coordinate transformations. And so again, using Pipeline Pilot and in this case the persistence of vision ray tracing freeware application, you can extend from doing planar transformations of a square to 3-space transformations of a cube. So there are some very direct analogies as far as what transformations are available and some new possibilities that crop up. So for example, the spherical transform doesn't really have an analog in 2 dimensions. And likewise, the inverse spherical, those are kind of extensions that are wholly different from what you can do in 2 dimensions. The polar coordinate transform really is quite analogous, can be easily mapped to the cylindrical transform, right? You just keep one of the dimensions constant and do a polar transform on everything. And likewise, the inverse polar and the circle inversion can be inverse cylindrical and cylinder inversion. So we have basically twice as many coordinate transforms now as we did before. And likewise, the symmetry preserving operations can be done against all the different axes, right? So that, again, even widens further the realm of possibilities of what one can do. And you can see down at the bottom here some of the single transformation operations. So the leftmost is the spherical coordinate transform, starting from a cube that doesn't quite fill the range where we're going to do this operation. And then the cylindrical, inverse spherical, and the sphere inversion. And of course, you can do this same sort of systematic exploration of the space. If you take the spherical transform and follow it by a rotation by pi/6 along the x-axis, if you apply that 2 times, you come to the lower left image. 3 times, 4 times, 6 times, and 10 times, you get to some fairly distorted and kind of difficult to visualize final geometries here, but kind of interesting and at least to my mind, very sort of organic, right? The way that these shapes become distorted and pushed and pulled, kind of like taffy or something like that. So back to how this is done. Here's a Pipeline Pilot protocol that takes the sequence of transformations, the code for a particular image, and runs it through a protocol that calculates where each starting point, which was on the surface of this cube, should end up at the end of all these operations. So we have a looping step here in this first exploded view, where we run through each We run through this once for each transformation that we need to apply. And then inside this sub-protocol, which is actually where the transformations are, there's basically a big case statement that says if the transformation's name is this, then run it through this component, which in turn actually carries out the mathematical transformation on each of the points that we're tracking. And typically I did this on about 250,000 points was enough to get reasonable resolution out of these kinds of operations. So you go through that a bunch of times until you've exhausted the sequence, and then you need to come up with some sort of visualization of this, the final output, right? Just looking at it as an array of points is not very entertaining. So this final sub-protocol takes the data that we've generated and generates something that's actually renderable out of that. In this case, it sets it up for rendering with the persistence of vision ray tracing application, and we generate a surface mesh for where the surface of this cube ended up, as well as some cylinders that highlight every 10th row or that sort of thing, and then points which are represented as spheres, which are sort of in the stood off a little bit from the surface, which are the normal to the surface at that particular point, or a little bit along the normal vector. So you can end up with images like the one shown on the left-hand side here, having gone through a large sequence of these transformations, showing the normals and where the surface of this cube ended up after having been squashed and stretched and put through the taffy machine, if you will. One of the other things that I found fun to do takes advantage of another capability of the Pipeline Pilot sort of generic components, which is the data clustering. So take the normals here, so this set of points that are, again, stood off from the surface by a little distance along the normal vector. In the final calculated result, so after we've put it through all these transformations, we take these normals and we cluster them. So we take the whole set and cluster them up into groups of 8 to 20 or so, and we take the centroids of those clusters and cluster them in turn, and so on up the chain. And then if you illustrate that with connections between the points, you can see in this detail image on the right-hand side, which shows the rectangularly selected area on the left, how various regions can sort of be broken down or divided up sort of hegemonically into zones. So I went through lots and lots of images like this, and eventually decided that it would be fun to look at some traversals of the parameter space in 3 dimensions, if I was just patient enough for all the calculations to take place. Wrote another protocol that would sift through all of the sequences and find ones that sort of went together, right? Because the discrete transformations, right, the polar, the inverse polar, the spherical coordinate transforms, those things, they really need to be in the same place in the sequence in order for the movie to be smooth and not have jumps, right? If you jump from spherical to inverse spherical, the whole image is gonna switch in the middle. So if you want to play movie number 3, this is at 30 frames per second, 45 seconds times 200 by 200 by 6 sides on the original cube. Something like 1 billion vertices have to be calculated in order to generate this animation. So this required a little bit of patience, but for some of them, the result was quite pleasing and worth the wait, I felt. There are more movies like that, as you might imagine. I have a YouTube channel. Okay, so a little bit early, but future directions. So there are still some operations that I have not implemented in 3 dimensions that I thought were particularly interesting in 2 dimensions, in particular this sort of chop, squash, duplicate operation that generates symmetries to add to the ones that preserve and destroy symmetries. Another thing that might be nice would be adaptive mesh resolution. So right now, the distance between points is fixed at the beginning, and so as some regions get stretched, the there are some very large panels, if you will, on the surface that gets generated, and it would be nice to add more resolution in those areas as we go through the stages. Longer, higher quality movies, yeah, that's just a matter of patience. Rendering, of course, is always something you can spend an infinite amount of time trying to figure out what would make these things really look nice. A lot of the renderings that I've done are really designed to show what the shape is, more than be necessarily particularly aesthetically pleasing. And so I've tried to do that a little bit. You can see in the lower center panel here, kind of trying to make it look like a real sculpture. So there's that. But then that brings me to 3D printing of some of these surfaces and volumes. So if we're starting with a cube and we're distorting it in various ways, it should be possible in the end to take that data and represent it in such a way that an additive printing approach can be applied to actually print some of these three-dimensional things out. And then you'd be able to look at them from all sides. And I think that would be a lot of fun. I'm going to work on that with the Fab Lab. But there's a lot of things that need to be fixed, I think, in my geometry before it's ready to be printed. And then the other thing that I've toyed with and almost have ready is a continuous generation online rating app. So all the pipeline pilot protocols generate web pages that the user, me, interacts with, and so it's actually possible to set it up so that every time one image is rated, another one gets generated, right? So you take you make it from a batch process into a flow process, a continuous process, so that as more ratings get done, you look at the most recent N images that have been rated, and you recombine a pair of those based on their ratings weighting, and then generate a new image. So as long as you stay ahead of people that are doing the rating, you could play this game forever, really, and keep going. Okay, one last slide. I want to just acknowledge Julie Bosson and Catherine Cousin for helping me put this together. Julie for the inspiration to actually do it and talk about this stuff and put the exhibit together in the tubes, and Catherine for actually making it happen. And if you are interested in more info or you want to work on stuff like this, I'm always looking for people to collaborate with. That's my email address. I have a web page, of course, and like I said, a YouTube channel where more of these videos can be found. So thank you very much. And if anyone has questions, I'll be happy to talk more about any of these things. Yeah.
You find some animals coming out of this generation, like early animals such as trilobites?
You know, I did see some forms that were reminiscent of what looked to me like some of the shapes of early animals. I think they would have to have been much earlier than trilobites. I mean, these are very simple, but you know, some of the algorithms that lead to the way plants and animals have their morphology laid out are really quite simple, right? Based on things like Fibonacci sequence or other very elementary kinds of mathematics. So yeah, I think that there's definitely some of that in there. I did have at one stage in the rating process an additional user interface element that had a bunch of different classes that were things like birds, fish, you know, insects, and things like that, where I was kind of lumping them into classes and trying to see whether there was pattern.
Do you think it's possible for you to work out algorithms that rate automatically?
Yeah, well, rating automatically is, that's tough. You have to decide then what you're going to rate based on, right? And I have tried it, but I haven't met with much success. So, I mean, you can rate based on trying to guess what amount of complexity might be visually pleasing, right? So there are actually tools in the imaging component collection in Pipeline Pilot that would allow you to assess how many vertical and horizontal lines there are and what's the average size of regions that are separate from each other, and other things that might inform the human eye view of, is this a pleasing shape or is this boring, right? But I haven't met with a whole lot of success. But if you could come up with such a thing, then you could do the whole thing as a closed loop, and you'd just pop out some beautiful image at the end, and that would be fun. But I find for myself that a lot of the fun is going through, and every image is a new thing, right? So you always can like have that experience on the next image of something really cool popping out. And that's part of what's kept me going with this, is that the rating process involves a little bit of discovery and kind of exploration of new stuff.
So which part of this work is most interesting for you?
Well, for a while, I was really engrossed with the evolutionary algorithm. That was fun to write and figure out how to optimize it so that it would really generate new stuff. I'm also enjoying kind of writing the three-dimensional coordinate transforms and figuring out what ones are out there that are interesting and useful. But it's the whole thing, you know. It's great fun. Other questions?
And I was wondering, did you also try to play with different scales? For example, using Fourier series to apply different flows to each scale and mixing them in the end?
No, I did not try that. That's an interesting idea. All of this work is based on applying the same transformation to the whole image every time. But it would be, I mean, you could try something like wavelets or something else that's sort of continuously scalable, and apply something like that. That'd be interesting. I haven't tried that.
And the second question, did you also try discrete transforms like subsampling or supersampling?
I'm sorry?
Did you also try discrete transforms like subsampling or things like that to have to introduce noise or blur in the pictures?
Yeah, so the only thing that I've done that introduces sort of texture or noise into the pictures is basically start with an image that contains that, or add this sort of transparent layer containing texture over top. But I haven't really explored that too much.
Okay, thank you.
Thank you. Did you try making other people than you weighting the images and see with different people after some generations what the diversity of the image they get? Mm-hmm. If one people from another, they get completely different images or not? Yeah, I have tried to engage a couple of people to do this stuff. Until I can get the sort of online system that's sort of very user-friendly finished. It required a bit of knowledge of Pipeline Pilot and a lot of interest and perseverance. But I did have one of my colleagues at BioVia in San Diego, Ben Acceleris, Ivana Mikic, who is the author of some of the imaging components, build it up and run some generations on her own. But I don't think she got particularly far. But I do expect that different people would have a different idea of what constitutes interesting paths to follow. And there certainly is, particularly in the 3D space, lots and lots of potential space there. It'd be fun to see. I'll be happy to share the components. Okay. Well, thanks very much again for your time and attention.